Hi everyone. In today's lecture, we are going to learn transformations. Okay. So far, we have learned the basics about robot, like what is a manipulator, what is the configuration of the manipulator, what are the components of the manipulator, what are the manipulator characteristics, and what are the applications of the robot, what are the standard configurations, what is the workspace, task space, configuration space, what are the joints and links, or I can say robot anatomy. Then we learned actuators and sensors. Okay, so we have learned all the accessories, but now we are entering into the actual robotess. Okay, suppose if I want to make a robot to pick an object from this point A, and I have to make a robot to move from this point to B. Okay, before to pick this, I should inform the robot that what is the position and orientation of that object. If it is a point, then there is no orientation. We need only position. So if it is an object, if it is an object or rigid body, we need to know the location. I mean, position as well as orientation. Why do we need orientation? Because the robot can grip like this, or the robot can grip in this fashion, or the robot can grip in this fashion. So we need to know the orientation of that. Okay. So how do we give the orientation and position with respect to one frame? So with respect to one reference frame, we need to say the position of this object is this, or the position of the object is this, or the orientation of the object is this. So for that, we need to know what is transformation. So we are going to learn transformation here. For that, first thing is, how do you represent a point in space? So how do you represent a point? Means it has three coordinates: x coordinates, y coordinates, and z coordinates. So that's represented over here. So we have three different planes, and these planes are orthogonal to each other, which is 90-degree to each other. This is the characteristic of this. And then a point is located. So if you want to say the location of the point, means straight away we cannot say. We have to say that the point P x direction is this one. The point P y direction is, so it is located this much far from x axis, this much far from y axis, and then this much far from z axis. So we need to give the position in terms of x coordinate, y coordinate, and z coordinate. So this is how we have to represent a point. So point does not have orientation, it has only location, which is position. Then how do you represent a vector in space? The same point, but when you give a direction to that point, when you give a direction to that magnitude, then it becomes a vector. So how do you represent a vector in space? Same way. The vector x coordinates and y coordinates and the z coordinates, and then the components of the vector is ax, by, and cz. Okay? And if I want to include a scaling factor. So how do I do that? So I have to multiply the x coordinates with one scaling factor w. Then that gives my new point. Okay, this is the scaling factor. So here we can check that. So this is the vector given. The scale factor is given. So just multiply 3 into 6, 5 into 2, and 2 into 4. So this is the new vector with the scaling. The scaling is applied. Scaling of two values applied. Okay, but original value is this one. This is your ax, and then ay, sorry, by, and cz. These are the points. So now I need to make the unit vector, because vector is always represented with the unit vector. Whenever you have a vector, it's good to represent that in terms of unit vector. So how do we do that? So for that, we have to take, so this is the x value. So the x value, then that should be divided by this 6.16. So how did you get 6.16? Just square it. So if you square this, 9 plus 25 plus 4. Okay, so it is 25, 29, 38. If you take square root of this, it becomes 6.16. So with this, we have to represent, we have to normalize this vector value. So how do we do that? 3 by 6.16, then 5 by 6.16. So that is here. Yes. Okay, so if you square this, if you square and add, then that becomes 1. That's why it is called as unit vector. So you have normalized the given vector to the unit vector. So how do we do that? So first take the square and find out the square root value, and then divide each value by its square root and get that. So this is the unit vector. If you take the squares and add it, and if you take the square root, it becomes 1. This is how we have to do the unit vector. So here the vector p is 5 units long and is in the direction of unit vector q. Okay, so it is described below. So this is this way, this x direction, y direction, but q we don't know. So how do we find it? So for that we can use a unit vector. That is why any position vector with the origin O and the point P. So the coordinates are x, y, z. So how do you represent using this unit vector concept? So that you can easily, suppose if one is missed, since it is aligned with the unit vector, normalized like a unit vector, you can easily find out the missing coordinates. For that purpose, it has to be converted into a unit vector. So we all know that. So this is the unit vector. Already they have given unit vector. And then how do we know the unknown value? By taking the square root of this, and that is equal to 1. So if you equate this to 1, so you will find out q is equal to 0.743. So this is 0.743. Okay. And then how many units? Scaling factor 5 units. So multiply by 5. So you will get the component. Okay. So this is one example. Then, so we have learned representation of a point in space, representation of a body in space, sorry, representation vector in space. Next one is representation of the frame at the origin of the fixed reference frame, representation of a frame. Okay, so here we can say that this is one frame. This is one frame. This frame has got new coordinates n, o, a. So this is a normal vector, orientation vector, and then approach vector. Okay, so we have to say that this frame position and orientation with respect to reference frame. Okay, so we are going to discuss that. So how do we do that? So here nx, so nx, ox, and ax, because this is the new vector, I mean the vector which is at the end effector. So it is in x-axis, this is in y-axis, this is in z-axis. So this is the frame. So the frame coordinates are this n axis in terms of x-axis, y-axis with respect to x-axis, a-axis with respect to x. Similarly, we have to give all the axes like y and oa with respect to y-axis and z-axis. So this is how we can give the frame. In this, we are going to check if if both the frames are merged at one particular point, and then one frame is displayed. So this is one frame, this is one frame. This frame is A frame, this frame is B frame. So we are going to rotate one frame. We are going to rotate this B frame with respect to A frame by an angle of theta, and then we are going to keep this as an axis of rotation. So the A frame Z and B frame Z are aligned, and with respect to that I'm going to orientate. Okay, so this is the orientation. So if this happens, what are the changes? Okay, so we have to take the same point, this is the point P, but we have to represent that point location with respect to A frame, and then the point location with respect to B frame. So how do I do that? First you have to fix the point. For example, this is your xy frame. Okay, and then this is your displaced frame. So this, let's say this is B frame, this is A frame, then here is the point. Okay, so first I have to locate the point with respect to this axis. So you have to do like this. So this is, so this one is x coordinate of this point, and then this one is y coordinate. Similarly, this point should be projected on this. So it should be projected on this. Okay, so like this. So we should know this also. Okay, so we'll see that. So first we'll see only the projection of point on the x-axis. So the point is projected on this. Okay, so I need to find out this x. Okay, so how do I do that? First I have to take this alone. So here theta. So I have, how do I write cos theta? For this cos theta is the entire x coordinates, the entire x coordinate. Okay, then divided by this hypotenuse. So hypotenuse is u. So this is u cos theta. So this entire point is u cos theta. But I want only this. So I need to subtract this value. So how do I subtract this? So you can use this point. Okay, this point is similar to this point. So how to find out this value? So here you have a theta, because here this orientation is theta between the y and y axis. So similarly here, so this orientation is theta. So this point is sine theta actually. So sine theta means it is v sine theta. Okay, So in this entire term, you have to subtract this. So that's why u cos theta minus v sin theta. We found one coordinate. The next one is y coordinate. So this is y coordinate. So here I'm going to put two sections. So this is first section, this is second section. The second section can be derived from this value, then the first section can be derived from this value. So let's derive this value. So suppose if I want to get this value, I have to take sine theta, okay, and then this hypotenuse is u, so this value is u sine theta, okay, and then both should be added. Then I need to get this value, then this value is cos theta. So you have this hypotenuse v, so that's why v cos theta. So we made x and y, and then z equal to w only, because both are same, there is no change. So now we will make a matrix. So x, y, z, so u, v, w. So first one is u cos theta minus v sin theta, the next term is 0. Similarly, the y coordinate is u cos sin theta, v cos theta, then this one, then this. So from this, we'll get the rotation matrix. So hereafter, if there is any rotation, if any frame rotation with respect to z-axis, in that case, your the values are, matrix values are cos theta minus sin theta 0, likewise. So this can be achieved by using this derivation. So we'll see one simple problem. A frame B is rotated by 60 degrees. So this theta is 60 degree, okay, and the point B, the coordinates of point B is this. So you have to represent that point with respect to A frame. So how to do this? So this is XYZ, we know the formula, okay? And then this is the point with respect to the B point. So just put cos 60 value and multiply, and then you will get these are the points with respect to A frame. So likewise, if one is given, if the other is not given, means we'll be able to find easily. Okay. From this, so what does it represent? So here we'll take, so here this is x, y, and z, okay. So here from this we'll understand that this is with respect to x-axis. So here this is with respect to x-axis, then this is A frame, the new frame is, it is displaced like this. So this is B frame, so this is theta, this is theta. So if it is with respect to x-axis means, then you have to displace and you can do the derivation, then you will get the answer like this: cos theta minus sin theta plus cos theta. So actually, so it is UVW. Suppose in this case, x should be the same value, so which is u, because x's corresponds to uv. So actually, x mapped with u, y mapped with v, and z mapped with w. Since it is with respect to x rotation, x-axis rotation, x equal to u. And then what is y? Y equal to, so you can multiply this. So this 0, so it is v cos theta minus, so w sin theta, okay. Likewise, z equal to u, sorry, v sin theta minus w c theta. So likewise, and then this is with respect to x-axis. So this is also x-axis, and then this is z-axis, which you have seen already, and one is missed, rot rotation matrix. In that it is rotated with respect to y-axis. So y-axis being 0, 1, 0, 0. So here cos theta, sin theta, minus sin theta and cos theta. So this is the matrix. So likewise, we will derive this derivation from this concept. Okay. So from this, what we understood is there are two frames. So both the frames origins are same. And then if one frame is rotated with respect to x-axis and the y-axis and z-axis, means the resultant frame is like this. And then its rotation matrix is this. Okay, so you have to remember this so that we can apply for any transformations to understand the concept easily. Next, we'll do one problem. The figure shows a frame B. Okay, this is the frame B. Okay, that is rotated from frame A by the angle of 30 degree. Okay, and then it is with respect to z-axis. So z-axis means 0, 0, 1, 0, 0. So here cos theta minus sin theta, cos theta. So this is the rotation matrix. Okay, then that should be multiplied by this point. From this point, which is translated to 2 points in y-axis, which means in x-axis no translation, in y-axis to z-axis it is 0. So just multiply. then in the place of 30, sorry, theta represent 30 degree and multiply, then you will get the new value, which is the point P with respect to A. Frame is determined. Okay. So we have seen that the representation of a frame with respect to the, when both the frames origin are same, but now we can see these are two frames, but see there is a distance between them. So there is a distance between them. In the previous case, you have this frame, on this frame only, or this is, so this is displaced. Okay, but here the origin is different, you have some distance, that distance is p. Okay, so how to represent this? The same thing, nx, yx, these are rotation matrix components, but this should be px. How far this point is displaced from x-axis, y-axis and z-axis. Okay, so now these 4 cross 4 is called as homogeneous matrix. So in homogeneous matrix, this 3 cross 3 is rotation matrix. This 3 cross 3 is rotation matrix. And then this one is translation matrix. So how to represent this? Any homogeneous matrix can be represented like this. So it has rotation matrix, it has translation matrix, it has 0, 0 and 1. So this is scaling factor. Translation matrix is 3 cross 1. 3 cross 1 is x-axis, y-axis, z-axis translation. I mean linear displacement, and then this is rotation, which is 3 cross 3. So this is how we can represent a homogeneous matrix. Okay, so this is one homogeneous matrix. So this is the rotation, this is the rotation matrix, this is the displacement, x displacement, y displacement and z displacement. Okay, and then we remember this equation. Okay, so now we'll see the problem. The frame F shown in figure is located at 357 points. Okay, with it n axis parallel to x and o axis, so n is parallel to x, so which means, so this is x, y, z, so this is n, so n is parallel with this, so you have a slight displacement. Okay, and then it says that 357, so this is wrong, so we can draw like this. So here x, y, z, and then this is n axis, this is x axis. Okay, there's a point P, so it is so this is y axis. Okay, this is, so this is the point P. Okay, so this distance is P, which is given as 357, and then this is actual y axis, so there is a displacement. That how it is displayed, o axis, so where is o, so this is n, this is o, this is k. Okay, so o axis at 45 degree from y axis, so from y axis the displacement is 45 degree. Then a axis, so this is a axis, this is original z, so this is displaced by 45 degrees. So if this is the case, how to represent the frame? Okay, so we know that this x-axis means you have to take this formula, instead of cos theta you have to put cos 45, which is 1 by root 2. This is sin 45, and then you have to give the translation. So this is how you have to represent the frame. So here also we can see that, so this point is 3 in x-axis, so you can see 3 point. Okay, from there 5 in y-axis, and then in z-axis it is 7. So likewise it is located, so this is ax, by and cz, so this is the new point. And then this point is located, I mean it is oriented 45 degree with respect to y-axis, it is oriented 45 degree with respect to z-axis. So like this we can represent a frame. So in this way, so this robot frame, this is nothing but your one of the robot frames. So likewise you can say where your robot is, what is the orientation of the robot, what is the position of the robot, using this homogeneous matrix. So once again I'll repeat, homogeneous matrix is a 4 cross matrix. In this you have rotation matrix, the order is 3 cross 3, then you have translation matrix, the order is 3 cross 1, is 0, 0, 0, and then this is one scaling factor. So this is your rotation matrix. So likewise we can represent any frame with respect to the world frame. Okay, next, how to represent the, because we have studied only the frame, but how to represent the rigid body, same thing, but apart from the frame it should be in the rigid body. For the rigid body also we can give the frame. So similarly your x-axis, so n frame, n axis, o axis and a axis. Okay, so the same concept whatever we applied for the previous case, that can be applied for this case as well. So now this is the this rigid body with respect to the world frame. So these are the orientation and then these are the translation. Okay, this is the scaling factor. Okay, so now we'll analyze. So since we have 16 parameters, because we have to solve this, then only we will understand how the location is. So for solving it, we have to use certain criteria. Okay, so in this, out of 16, we can neglect this because 0 and 1. So totally you have 12 constraints. So 12 equations you have to solve. How to solve? So in this, already we have discussed x, y, z or orthogonal to each other, which is perpendicular to each other, which means all the unit vectors n, o, a are mutually perpendicular. And then one more thing is each unit vector's length is represented by directional cosine, that is cos theta, and then that must be equal to 1. Okay, so these three, so here unit vectors means these three, and then this vector length is 1. So totally it is 6. So now you're 12. If you apply this, because we know the value, we know this, the unit vector is 1, and then we know that is perpendicular to each other. Perpendicular to each other means dot product is 0. Okay, so since it is perpendicular to each other, n dot O. So this product is 0, this dot product is 0, this dot product, sorry, this dot product is 0. So totally three equations. So so your 12 is reduced to 9 now because of this three equations. And then another three is, since it is a unit vector, so the magnitude of n vector, O vector, A vector is 1. So totally we have applied 6 constraints. So 12 minus 6 equal to 6. So we have only 6 more constraints. Okay. So likewise, we can decrease the number of constraints using the standard property. Okay. So now, yeah, these are the things. So the remaining equations, see how to do this. So this is your magnitude equal to 1, and then this is your dot product equal to 0. Okay. So with this, we can determine the rotation matrix. Rotation matrix first concept is all the three axes are orthogonal, then only we can apply the other parameters. So orthogonal to each other. That's why each row and column or column of rotation matrix is a unit vector because they are orthogonal to each other. Okay. Since it is orthogonal to each other and also it is a unit vector or perpendicular to each other, the dot product is 0. So once you assign orthogonal, then automatically the other two properties are on the way. So first one is it is orthogonal to each other. Second point is each row or column of rotation matrix is a unit vector. The next point is the dot product is 0. The same is true for each column also. So these three properties. Apart from that, the rotation matrices are not commutative. That is, if you change the order, then that is not equal. So remember this. So rotation matrices are not commutative. So if the rotation matrix or if any matrix is not commutative, or if it follow the properties, we can directly declare that matrix as a rotation matrix. So it is not commutative. So remember this point as well. And then the rotation matrix speciality is, if you want to take the inverse, just take the transpose. If it is a normal matrix, how do we do that? We take a determinant of that matrix and then we calculate edge of that matrix. Then only we'll get this A inverse. Okay. Whereas in rotation matrix, just take the transpose. You know that the rows are interchanged with columns. So these are the properties. And one more thing is the determinant value of the rotation matrix is always 1. So these are the properties. So first one is it's a orthogonal to each other. That's why each row or column of a matrix is a unit vector. And then dot product is 0. And then this is not commutative, and then the inverse is equivalent to transpose of the matrix, and then determinant of the rotation matrix is 1. So these are the properties of the rotation matrix. So with this concept, we'll solve this problem. So here, this is the matrix, this is a frame matrix is given to you. We have to find out the unknown values using this equation. So already we know that, so each dot product is 0. Okay, so nx yx, this one, similarly this, and then similarly this. So we can have 6 equations. Okay, and also one more equation is, yeah, this is 3 equations dot product. Then since it is a unit vector, then normalize that value is 1. So using this we can solve. So here I have solved this. So you can just multiply and then take the common terms, or you can resubstitute the values, and finally I will get these values. Okay, you can slowly go through later. Okay, so these are the values we got from that. Okay, and another point is the same problem can be solved with the help of because since it is orthogonal to each other, n cross o is equal to a. So how to do that? So this is the n values, and then these are the o values. So we can get this matrix, this vector, then just multiply and substitute the values. Then from that you will get some equation, then solve this. So you can solve in the other way or in this way also. This is also one more problem. You can try.